who's CEO of PragmaDev, and I am a second-year master's student at SCA Paris. This particular translation that I did was part of an internship that I did at PragmaDev, and it was, let's just say, a very short-term project. So this translation that we have here is kind of going to be a very basic but correct one. So what is translation? Why do we need such a translation? SDL, as we know, is a modeling language. Fiacre is a pivot language. And the need for a modeling language is because, of course, the modern day embedded systems are increasing in their complexity by exponential terms. So we need some kind of formal modeling language in which we can define our system, at least in terms of specifications or design level, or some abstract level that are correct to in terms of their application and what they mean. And in that sense, SDL is a formally defined modeling language, so you can have an accurate description of your system. The second important point is, of course, critical systems, like as we saw in the previous presentation. There are a lot of properties, a lot of limit, a lot of directives that you want to give to your software that it needs to follow in terms of properties, or in terms of critical failures, or in terms of memory constraints or other things. So we need certain property verification tools. We need certain criteria to be satisfied in all times. In that case, we need some kind of property verification tools. So we have, using the translation, we can have use of those translation. We can use the translation in Fiacre for a verification tool. Then, of course, there's a need of formal methods in various industrial certification standards. Of course, the DO standard has been for quite a long time, so we have seen a lot of usage of that in aeronautics, and in recently, maybe not recently, but in the last few years, there's also sometimes recommendation or even mandatory use of some kind of formal method in their software development process for certain critical systems in these fields. SDL, of course, as I said, SDL is a formally defined modeling language standardized by the International Telecommunication Union as a Z100 recommendation. It's object-driven and event-driven. Object-oriented and event-driven. Of course, that's critical in terms of when you have development for embedded systems or control systems. It has a graphical and textual format, so you can define graphically what you want, or you can export it as textual format for various tools and input to various export to various tools that use an SDL description. It's also used as a real-time design language in many projects, many software designs, protocol designs, things like that. Additional real-time embedded support is there in SDL 2010, the latest iteration of SDL. So you can have advanced features that you can use to model real-time embedded systems. And of course, it can be easily interfaced with other languages, ASN1, UML, of course, and for testing, you have PTCN3. Fiacre. Now, what's Fiacre? Fiacre is basically an intermediate language, a pivot language. As such, Fiacre is nothing. But when we have Fiacre, we get a gateway from DSML, a domain-specific modeling language, SDL, SysML, AADL, to the domain of formal verification. This language was developed by the team of Lars, Inria, and Berit. And also in the framework of Top Case project, which is a project by Airbus, and it was made to incorporate model-driven development in their own tool chain. So all these teams from various research institutions and the team from Airbus were the ones to define Fiacre. It allows, of course, it to be able to use in such embedded real-time systems. It needs to have some kind of semantics which are helpful in developing, or at least specifying, the semantics of a real-time embedded system. So it has behavioral and timing aspects of embedded systems and can define them. Now, another important point about Fiacre is that it can easily be used by the following tools: TINA by Lars, CADP, of course, by Inria, and OBP-CDL by Instability. Now, these three tools have been there for quite a long time, especially CADP, and they have straight-up functions which can import a Fiacre file and then perform model checking or other kind of analysis on the Fiacre file. There are three main objectives of these translations. First of all, of course, to preserve the semantics of SDL. So you need to preserve what you have in SDL, what you defined in SDL in terms of schematics of SDL language, we need to preserve that in the Fiacre description. The second point is, of course, the verification of the system using one or more tools as possible. A Fiacre file doesn't mean anything unless it can be verified using any of these three tools. So we need to have a certain tool that can take the Fiacre file that we generate using the translations proposed here to be able to verify the system. And of course, the verification results are, to the very least, observable. I mean, we of course try to have a loop back or some kind of graphical notation or some description in terms of an SDL model, things like that. But at least in terms of the ground of work that we have done in this translation, you need to have the results observable. So the first translation will, of course, start with the architecture. The basic architecture of SDL description is a multi-level hierarchical structure. You have blocks, and then you have processes, and those processes you have state machines, finite state machines. So a hierarchical structure is, of course, a part of SDL, which needs to be translated in a Fiacre. But Fiacre doesn't allow such multi-level hierarchy. It needs more of a flatter, simpler structure. It just allows for a component and a process, just two basic structures which can be used. So we need to have some kind of translation to simpler structure. So you just used components, which just analyze and which more or less initiate the different processes in terms of their declaration. Communication. The main key aspect in SDL communication is asynchronous. So we have asynchronous communication that we need to preserve. And to do that, we used to use the basic data structure of a queue and array, and of course we used globally shared variables. Now these globally shared variables can be separated from sharing between different processes by the use of components, like I said in the previous slide about hierarchy. So you have controlled sharing of the globally shared variables. State machines and data types. In SDL, you have extended finite state machines, and you have lots of predefined data types, which allow for good expressiveness in terms of system modeling, but it's a difficult task to translate in the Fiacre language, as it's a very basic notation of the system. So we have just processes, which are behavioral or sequential components, using decision statements, blocking and non-blocking, like if, else, and what, on, things like that. So it allows you to just straight up finite state machines are there in Fiacre as processes. Of course, Fiacre again has a very limited data types, just integer, natural, and Boolean, but it can be counteracted by the usage of various custom data types, and you can create elaborate data types that you can use. And of course, array, queue, and union, basic structures that you can use. So that allowed for, at least in terms of the limited functionality that we had, to express the extended FSM of SDL in Fiacre. Here's a basic schematic of the tool chain that we actually implemented in the PragmaDev tool, PragmaDev real-time development software. We have a system in SDL, this is a description in SDL, basic SDL. It goes to PragmaDev, which has all the translation rules that we defined, and they automate the translation of an SDL system into a Fiacre file. So we have a Fiacre file.fcr. In the Fiacre file, you add the properties for the verification. Now, Fiacre allows to write properties in terms of Fiacre, just say language. It's a basic LTL notation, linear transition logic notation, but you can write it in a more simpler manner if you understand what's there in the Fiacre file. So it is a bit less mathematical, but still, if you understand the Fiacre file, it's easy to write. There are a few examples in the proof of concept, and you can see it's a bit easier than a mathematical operation at least. The Fiacre file now goes to the TINA toolset that we used in the proof of concept and the schematic and tool chain that I'm going to give after this slide. We use the TINA toolset. So we have our Fiacre file, we have our properties that we write, and that is given input to the TINA toolset. Now, TINA toolset has many functions. Three of those which we use here. First is frac. Now, frac converts the FCR file into a time transition system and the basic LTL properties. Now, LTL properties are just those mathematical properties that we just wrote in Fiacre format. And the time transition system is the abstraction of Fiacre file that TINA needs to analyze and model check. Now, in the TINA toolset, there's a tool called TINA, which then takes as input the TTS time transition system and converts into a crypt key transition system, which is very basic in terms of model checking. And it takes and so we have a basic abstraction of a crypt key transition system, and we have LTL properties. Those are given input to CELT. CELT is a state event LTL model checker. which takes in the criticalization, of course, and LTL properties, and gives us the verification results. This is a very basic, low-level model checking, simple model checking in terms of the formats used and the methodologies used. And you can see basic screenshots of how the tool has been integrated into the PragmaDev.ts. You can either export it as a Fiacre file, a simple Fiacre file. You can either use CADP and other tools to use, or you can go to the preferences, which is basically you call a script which calls the tool for you, and then you can verify. So we have now present a basic proof concept, a simple race condition, nothing special. This diagram here is a basic SDL model that we have in PragmaDev.ts again. So we have 4 processes, 1, 2, 3, and 4, and we have an environment process. The idea is when we send, so first the environment process is made to send a message go. We send go. On receiving go, the process 1 sends 2 different messages to P2 and P3. P2 and P3 on receiving the 2 messages respectively send out M2F and M3F. So you just have initiation from process 1, then to the process 2 and 3, and then they forward the 2 messages, and then they're received by process 4. Now the idea is in process 4, only when you receive the 2 and 3 in a certain order, then only you will be able to send a message done from process 4. A basic race condition to the very extra. And here we have the basic SDL process, SDL extended FSM diagrams of the different processes that we use in proof of concept here. So we have P1, P2, P3, P4, and then the environment process. So you can see it's sending a go message, then it's receiving a go message, sending out 2 different messages. It's receiving M2 and it's sending out M2F. It's sending P3 is receiving M3 and it's sending out M3F. In P4 you have M2F and goes to intermediate state and then M3F and then send out. So if you receive these 2 messages in different order, it doesn't work. Now the properties that I wrote to verify this system are basic simple LTL properties in Fiacre format. The first, of course, is basic deadlock property. The property, you can see how simple is right. Property, then the property name, which is DDLF, is deadlock free, which is a keyword in Fiacre format, and assert DDLF. Property. Now the second property was the main that we wanted to verify for this proof concept, and it says that receiving go in process P1 leads to done being received in PENB, which is the environment process. So we have property. Name of the property is system 3 state, which is basically a specifier that in which system, which is the abstraction of the whole Fiacre system. Number 3, which basically gives the order of the process that we have defined. State is the state in which the process should be. And state is basically, you can also verify on various other things such as messages. You can also test messages in this. So you can say message, it should be a particular value. Leads to, so it leads to is basically a LTL format, and it says this state idle should lead to this state, and you have assert. So basically you're saying is if a particular process in a certain state, it should always lead to a certain process being in a certain state. And so the results of the model checking using TINA were as expected using LTL, SELT, which was basically, like I said earlier, a state event LTL model checker. And of course, both properties will verify as false. SELT again generates a sequence of transitions in TTS format. In TTS format, but although it's a bit difficult to understand, but manual verification is possible, and so it generates a sequence of transitions as counterexamples so that you can verify that the property that you were checking actually was indeed false. A basic idea, the diagrams that TINA generates, on the left you have a crypt key transition system. It's a whole extensive state space of the system that we made. On the right we have a time ptnets description, which is basically what initially is translated from the Fiacre file. So here we go from time ptnets to a crypt key transition system, and then on the crypt key transition system you have the model check. Some remarks we have here is, first of all, of course, the user needs to model an environment process. In SDL, you have an environment there present for you. So you don't need to model an environment process, you don't need to make one, it's there and you can connect it and it works automatically. But for the purposes of this model checking purposes, you need to have a complete system. You need to have cycles, you need to have extensive state space. For that, you need to have an environment process. I mean, we could have model one automatically for the user, but to have an accurate description of the system that the user needs, we ask the user to model an environment process. Of course, number of states and transitions are to be kept as low as possible. The biggest problem in model checking is state space exclusion problem. It needs to be counteracted by keeping the states in transition as low as possible in the translation rules. And we try to do that as far as possible. The feedback of the results from the TINA tool back to the SDL model, that was initially one of the things that we explored, but it was not possible. Probably because of there are two more translations even after Fiacre 5. So you have TTS and then you have cryptic translation system. So the semantics of the language changed to the levels that it was not possible to parse it automatically and then generate a SDL description or something. It can, although we parse manually, so as to verify that the properties that you were actually asking to verify were verified in fact. So to conclude, translation rules from SDL to Fiacre were written and verified. We did verify in terms of the whole proof of concept, and we made a proposition for a few other concepts of SDL. The proof of concept that we accomplished confirmed that not only the translation works, but also SDL models can be verified with using Fiacre and those tools. Now, of course, some other verification tools like CADB or OBP-CDL could have been used, and they might have given different results, but they're part of future study of that. And as a matter of fact, currently this translation is a very basic one, and currently PragmaDev, they're working on improving this translation to have better translation and more extensive translation in terms of SDL concepts. Thank you. Any questions?